Yeah. Can you see the entire screen now?
Yes, sir.
Oh, thank you. Okay. So I'll just yeah. Working. Okay. So today I'm going to present this talk, Eyes on the Sky, Current and Upcoming Telescopes of this decade. So basically, we know all about the telescopes, what kind of telescopes we have, and what are the telescopes that are operating currently. So this talk is meant to shed some light on what the current state of the art is in terms of telescope technology, and what are the upcoming telescopes that we can see until this decade ends, right? So before we go into telescope, let's say what is astronomy, right? So how do you define astronomy? So one way to define would be this: astronomy is a science which studies the objects beyond planet Earth. But earlier we used to have multivariate astronomy, but now it has shifted to multi-messenger astronomy, because on the right that you see here, so we have gamma rays, we have neutrinos, we have cosmic rays, and we have gravitational waves, right? So not only photons, but all other sources of information is also available in terms of these many messengers right now. So now multivariate astronomy is not the norm anymore. Multi-messenger astronomy has taken over, right? So what kind of multi-messengers you can expect? So one is photons, obviously. So photons will be divided depending on the energy. So one is the gamma rays will be the highest energy photons up to radio wavelengths. Then you have the neutrinos, and then you have the gravitational waves, which is most recently developed technology. And obviously we have the cosmic rays, which have been observed for quite a long time now. Right? So now, why do we need to do astronomy and astrophysics, right? So what kind of development or unique contribution astronomy provides in terms of our understanding of the nature? So the first thing is testing the laws of physics. So we are talking about extreme energies here, higher wavelengths, comprehensive wavelength coverage and all. So only astronomy provides you these, like if you talk about the gravity, if you have to test the Einstein's law of gravity, so on, you have to look around objects, massive objects like a black hole, right? Then obviously we can discover new objects. So each day, new galaxies, new stars, new planets are being discovered. So it is broadening our horizon of understanding of the sciences. We can obviously do cosmology while only through astronomy. So cosmology helps us understand our place in the universe. And another aspect of astronomy is understanding our neighbors. So the biggest challenge is whether we have life on other planets or not. So only through astronomy we can do. Then obviously the currently we have a problem of space debris. So as you know, a lot of spacecrafts are there in the sky, a lot of telescopes are there, so a lot of junk would be there in the sky itself. So understanding these space debris through only we can do only through telescopes, like we can detect debris and then try to mitigate those threats and all. And then obviously the holy grail of astronomy would be finding another civilization. As you know that currently we don't know any civilization other than planet Earth. So if we find any other civilization, then obviously we have to rely on astronomical techniques and astrophysical understanding. Right? And if you look at this image here, so this is an artistic impression of Oumuamua, which is very difficult to pronounce it, and it is probably the first interstellar object that is observed in our solar system so far. And it is a very mysterious object which has not been studied so far, and people do not know where this came from and then where this went itself. So if you're interested, maybe you can explore it further. Now, once we establish why astronomy is needed, so we cannot do through naked eyes. So we need telescopes. So why do we need telescopes? If you look at the sky, so objects are classified based on their magnitudes. So the sun is as you know, the sun is the brightest star that we have, the brightest object that we can see in the sky. So the magnitude of sun is minus 26.7. If you look at the full moon, the magnitude is minus 12. And Venus, if you look at the brightest part of Venus, it's minus 4.4. And if you are in a city like Kolkata or Delhi, so the naked eye limit is like plus 3 magnitude only. And if you go to far off places like the Himalayas, you can see right up to plus magnitude 6.0. So this is it that we can get from the eyes. And now if you have a binocular with you, so the faintest thing that you can see is plus 9.5 magnitude. While if you look at a telescope like the Hubble Space Telescope that we have in space, so the magnitude faintest that you can see is plus 30. So you can see the kind of jump that we are making from the naked eye to the telescope. And this is all in logarithmic units. So people who are not aware, so this is not 2 times, this is rather 1,000 times. So 3 to 6 is like 10 to the power 3, so it's 1,000 times fainter. So 6 to 30, you can imagine how fainter we are looking at. So obviously telescopes help look us farther and deeper into space and to look at the planets and the stars as they are, which we cannot observe through our naked eye. So this is a prototype of the first telescope that was used by Galileo Galilei, and this is the one that you know. This is the Hubble Space Telescope that is operating since the past 30 years, more than 30 years, in fact. And this is the cleaning process of one of the largest telescopes that is going on. So you can imagine this is the human, and this is the kind of mirrors that we have developed. This is one of the telescopes that we'll see in the next slides. Now, people who are not familiar with different wavelengths, so you know that the optical, the photons can be divided into different wavelengths, and optical is a very narrow window of that wavelength. So if you divide the entire photons into this kind of regime, so this is your radio, and this goes from the highest to the lowest wavelength. So radio can have wavelength of 1,000 meters, 100 meters, and all. And the sky is not very familiar, not very familiar to us in the sense that it does not allow a lot of photons to pass through it, because atmosphere acting like a window, which is not allowing different wavelengths. Like if you have microwaves, if you have this X-rays and gamma rays, so you cannot observe them from the ground-based facility. So you have to go to space. So if you're observing in microwaves or the X-rays or the gamma rays, even some radio waves, so you have to go to space. While you can only do optical visible photometry observations from the ground. So different wavelengths require different kind of telescopes. This is why we have a mixed combination of both ground and space-based telescopes in the current scenario that we have. So now, why would you need to have the telescope in the space or ground? So anything from the space would be much beneficial, would be better. You get better conditions, you get better resolution, so obviously you can see fainter. So why don't we have everything in the sky, right? So problem is with the space is it is too costly, right? So you cannot send this telescopes randomly into space. So sending a telescope in space would be costlier than setting up 100 telescopes on the ground. Right? And if you look at the electromagnetic observations that we do, so we have only two modes of observation mainly. So one is direct imaging, the images that you see on the right here. So these beautiful images that you can see, it can be obtained using the ground-based telescope itself. And the other mode is spectroscopy. So basically, you look at this image and then you try to dissolve the elements inside it, and it looks something like this. So in the spectra, basically, you have lines, so you can identify those lines and then try to understand what kind of composition this thing has, and what kind of objects are, what kind of elements are available in that place. So that you cannot do by looking at that image. So for those things, you need to go for spectroscopy. So now, if you look at the current scenario of ground-based telescopes where we stand, so this is the map of almost all the large telescopes that we have. And if you look at the largest telescope right now, so this is the VLT here. So it's 8 meter into 4. Then you have the this Magellan telescopes in Chile. You have the Large Binocular Telescope. You have the SALT, Hobby Ability. So these are all 10-meter class telescopes. And on the left, you see these are all 3 to 4 meter class telescopes. And these are the upcoming facilities that we have. So the obviously the Vera Observatory will be coming up. The GMT will be coming up. Then there will be the extremely large telescope, which is planned in Chile. And then obviously there is the 30-meter telescope, which is planned in Hawaii. And for reference, you have this. This is one of the tennis courts, and this is the basketball court at the same scale. So you can imagine the kind of leaps we have made in telescope technology in the past few years or so. So currently, obviously the ELT 42-meter telescope is the largest telescope that is being constructed currently, and it will be online within 3-4 years, we expect. So how size matters? I mean, you might be thinking, why do we need such large telescopes? So obviously, it's all about the light gathering power. So if d is the diameter of your telescope, so d squared divided by 4 is the diameter. So if the telescope is 1 meter, so it will be like 1/4. If it is 4 meters, so it will be 16/4. So 4 times. So by increasing the diameter by 4, you increase the light gathering power by 4. And imagine if this is 10, so this is 100/4, so 25. So if you go from 1 to 10, so your light gathering power is increasing by 25 times. So you can see objects that are much fainter than you would see with a 1 meter or 2 meter class telescopes. So this is why we are going for larger and larger telescope apertures. So now I'll just briefly go through what are the largest telescopes that we have. So first we will go through optical. So what are the optical telescopes that are about 10-meter class set up in the world? So one of them is the Large Binocular Telescope. It was set up in 2005, and it has been operated by the Monograph Observatory in Arizona in the USA. And it has made some remarkable discoveries, like the one you have the galaxy cluster, this 2XM083226 was observed in 2008, which is about 7 billion light years away from the Earth. So you can imagine the kind of distances it can see. And it can also observe some very faint objects, like it observed at 26th magnitude afterglow from the gamma ray burst. So the eye is 6 and this is 26, so you can see what kind of faint limits that it can go. Similarly, there is the pair of telescopes in Hawaii. This is the Keck telescope, again operated by the USA, and it is located in Hawaii, and it has been very instrumental in developing the planets outside the solar system. And it has also provided evidence for the model of the Big Bang theory that we know. And this is the telescope set up in other places. So on the left, you see the 10-meter GTC telescope set up in 2007. It is located in La Palma, Spain. Okay, I forgot to tell you all these locations on the map. So all 10-meter class telescopes you will find are located either here in the La Palma, here in the Hawaii. This is the Chile location. This is where the European telescopes are there, and several telescopes are located in the USA. And one telescope is here in the South Africa. This is SALT. So only 4 or 5 locations across the world have these facilities of the largest telescopes greater than 10 meter. So similarly, you have this 10-meter Hobby Ability Telescope, which was set up in 1996. Again, it is operated by the USA McDonald's Observatory, and it has been instrumental in discovering the dark energy, proving distant galaxies and black holes, etc. And it has also set up a dark energy experiment to look for dark energy and dark matter that we are looking for, but no evidence has been obtained so far. These are other two telescopes of 10-meter class. So one is the SALT. Sorry, there is a fighter jet above us. It's gone now. Sorry for that. So we have the SALT telescope that is set up in 2005 and is operated by the South African Astronomical Observatory and located in South Africa. And it has also been instrumental in discovery of a class of star which is known as the polar or a pair of T stars. So each telescope has made some remarkable discoveries which we can say that this has been unique in sort of this the contribution has been unique. And this is operated by the Japanese people, set up in 1999. This is again located in Mauna Kea in Hawaii, where the telescopes are located. So these telescopes are what make the largest telescopes that we have currently. And obviously, the VLT is a very state of the art kind of telescopes. So VLT is very unique in the sense that it is a set of 4 8-meter class telescopes. It has started operated in 1997, operated by the European Southern Observatory, which is a consortium of about 21 countries, and it is located at the Paranal Observatory in Chile. And many remarkable discoveries like stars circling around the supermassive black hole at the center of Milky Way, which was awarded the Nobel Prize to Anja Gaze. So this discovery was made using this telescope itself. And then again, we have the Gemini telescope. So Gemini is basically a pair of telescopes in, so one is north, one is south. So northern one is located in Hawaii and southern one is located in Chile. So these two telescopes operate as a pair. It is again operated by the United States of America. Now, once we review the optical telescopes, it comes to radio. So in radio, things are a bit difficult because in optical, you have very limited wavelength coverage, while in radio, there is a huge wavelength, right? So, I mean, there is no particular band, there is no particular wavelength window which you can observe. So basically, radio people talk in bands. So you might have heard this 325 megahertz, 1.4 gigahertz. So these are all radio telescopes are tuned to a particular frequency with a range bandwidth itself, and each telescope is operating at a particular frequency and band itself. So, and radio signals are quite weak, so you have a receiver which will amplify the signal to a measurable level, and then you have a recorder to keep a record of the signal, and a computer which uses the data to process and analyze. So the radio data is not as easy to handle as the optical data. So on the left you see the rate. Okay, so on the left you see the radio sky over here. So nothing is visible if you look at the naked eye, right? But if you can make out the radio fluxes from these objects, so you can get beautiful images like this. So these are lobes observed in around a supermassive black hole in an active galaxy. So now if you talk about the radio, two very large facilities are operational currently. So one is operated by the USA, other is operated by the Europeans. So the ALMA is operated by the USA. It is about $1.4 billion. So it is the most expensive telescope in operation right now. And ALMA can go from 3.6 millimeters to 0.3 millimeters. So if you convert the wavelength into frequency, so it is ranging from 31 to 1000 gigahertz. So you can imagine the kind of wavelength coverage it has. And ALMA basically is a network of telescopes. So 66 telescopes are in operation in ALMA. Similarly, the VLA is operated by NRAO, the National Radio Astronomical Observatory in the USA, and it has 25 meter radio telescopes. So each of the telescope will have 25 meter of diameter. The frequency is again 74 megahertz to 50 gigahertz. So you see, this is quite limited as compared to the ALMA. So ALMA has much more coverage. And these two telescopes has done large amount of radio surveys. So all the public radio data that you have, it is likely that it has been observed from these two telescopes itself. So recently, a telescope was developed by the Chinese people. This is the 500-meter aperture spherical telescope. So this is a very unique kind of telescope, like in the sense you see these are arrays. So this you need a large baseline for radio. So these arrays can form a baseline. But instead of array, if you have a valley, so you can make the entire valley as a telescope. So this valley has a diameter of 500 meters. This is the first telescope that is operational in China, and it has the frequency of, again, very large frequency range, 70 megahertz to 3 gigahertz, and it has observed many things, like it is involved in the pulsar observations. This is leading the international very long baseline interferometer network, VLBI. You look at the southwest of China in Guizhou, and it started operation in 2016. In India, we have a very beautiful telescope which is known as the, again, this is the fighter jet. Oh, my audio is fine, right? Can
Yes,
anyone
sir.
come?
Yes, sir. Yes, sir.
Okay, so there is a fighter jet circling around. I mean, this is interrupting. I'm sorry for that. Yeah. So this is the GMRT in Pune. And actually, I am nearby to this telescope right now. So this is operated by TIFR, and this has 30 fully steerable parabolic radio telescopes of 40-meter diameters. So each one of dish is 45 meters. And the uniqueness of GMRT is that it is operating 6 frequency bands centered around 6 frequencies. So ALMA has a large wavelength coverage, but then again, it doesn't center on the fixed bands, and these wavelengths are not covered using ALMA or VLBI or the VLA. So this GMRT makes it quite unique, 50, 153, 233, and this is a very unique telescope which is searching for the highly redshift 21 centimeter line, which has been a very remarkable discovery from this telescope. It is operation since 1995, so about 30 years of operation. It has published remarkable results so far in radio astronomy. Now, if you talk about the radio astronomy, so there is a network of telescopes known as the Event Horizon Telescopes. People who follow science might be very familiar with this one. So it is a global network of radio telescopes which is located across the globes. So instead of the baseline of a few kilometers, this makes the baseline of the entire almost half of the world. So you can imagine the kind of baseline this telescope has. And this telescope has been used to resolve two very nearby objects. One is the M87 shadow of the black hole, and this is again the Sagittarius A of the black hole, which is, these two images have garnered quite a lot of public imagination and praise as well, because this is one of the telescopes which is very remarkable indeed. This has been the first telescope to image a black hole using this Event Horizon network. Another kind of telescope is the LIGO. So you might be aware that LIGO is located in the USA, and this has been only recently, 4 or 5 years ago, this had detected the first ever gravitational wave, which is predicted by the Einstein's theory of gravitation. And this LIGO, obviously, it has won the Nobel Prize in 2017, and this is the ripple signal that won the Nobel Prize. So you can see that there is the perturbation through the gravitational wave in the signal. So this is another new dimension to our observations, and India is also making a new LIGO detector of its own, which will be helpful in detecting many gravitational waves in the future. Now, if you go to space, so as I told you that the only optical and IR probably are possible from the ground. And while if you have to observe in gamma rays, X-rays or UV, you have to go to space because sun is, the atmosphere is blocking all the wavelengths that you say. So multiple telescopes are operational in the space currently. This is a map of all the telescopes that are in the space right now. And so different kind of orbits are there. So you might be, these are low Earth objects like the Hubble Space Telescope or on Astrosat, the Fermi. These are all on low Earth orbit. So a few minutes of orbit is there in these telescopes. These are polar orbits. Then again, you have the Lagrange point. So this is the L2. So similarly, you have the L1 Lagrange point where you might have heard that the Aditya mission is going. So this is the L1 Lagrange point here. This is the L2 Lagrange point where the JWST telescope is located. And the different telescopes based on the different science cases are located all across the sky right now. So if you talk about the space-based X-ray telescopes, so 3 telescopes are very popular right now. I mean, they are still in operation, and they have detected many things. Multiple papers are there. So Chandra is there, launched in 1999 by NASA, and Swift is there, launched in 2024 by NASA, and the New Star. These all 3 telescopes were launched by the United States. And similarly, you have the European counterparts. So this is the XMM Newton, launched in 1999. And XMM Newton has been very successful. It has resulted in about 5,600 published papers so far in the past 25 years. Similarly, you have the Integral, and then you have the Fermi. Fermi again launched by NASA itself. Our own Indian contribution is the Astrosat. So this is the India's first detected multivalent space telescope. It was launched in 2016 on board the PSLV, and it observes in X-ray, UV, and optical bands. There are multiple instruments on board for different wavelengths, and it has made multiple exciting discoveries, like you have extreme UV wavelength from a galaxy located 9.3 billion years away from the Earth. has also observed variation in X-ray polarization of the Crab pulsar, because this is one of the unique telescopes which is carrying X-ray polarization instruments. So main discoveries. Now, as I told you, the optical IR astronomy can be done from the ground, but obviously the ground-based resolution is poor, so it is always a need for space-based optical telescopes. So two telescopes are very, very popular currently. One is the TESS. TESS is the Transiting Exoplanet Survey Satellite. So it is launched in 2018 by NASA, and it was a direct successor of the Kepler mission, which was intended to detect exoplanets. And the TESS has 400 times more area coverage than the Kepler, and it has already confirmed 273 exoplanets so far, and about 4,000 candidates have been discovered by tests. So these are all exoplanets. So this is all hunting for life. So maybe on someday we can find some life on these planets. Similarly, we have the Gaia. So Gaia was launched in 2013 by ESA, the European Space Agency, and it is the UV2 IR telescope, and it is the largest and the most precise space map ever created. It has created the most precise map ever, with consisting of about 1 billion space objects so far. So Gaia was designed to be a survey. It has surveyed about 1 billion objects so far. So you can imagine the kind of work these telescopes are doing. And obviously, this is the most popular telescope that we have right now. So it was launched into low orbit by NASA in 1990. So it has UV, optical, and IR mirrors. And you can see the primary mirror is only 2.4 meters. So we are talking about 30, 40 meter telescopes on the ground, while Hubble Space Telescopes only 2 meters can produce such beautiful images that even 30-meter class telescopes cannot. And it is the most popular observatories ever. It has spent about 32 years in space, and you have many, many exciting discoveries, remarkable photographs from the Hubble, like you'll see a couple of photographs here. So these are the kind of beautiful images that has been captured by Hubble Space Telescope. So these are all nebulae. This is only possible from the ground-based or from the space-based observatories because of the limited resolution that we have from the ground. So now the successor to Hubble Space Telescope is the James Webb Space Telescope. It is observing in IR, not in optical, because of some different science cases. But again, the diameter of this telescope is 6.5 meters. So it is like 3x more larger than Hubble. It is operated by the STCI Institute in Baltimore, USA. It is located on the L2 Lagrange point, and multiple results have been already obtained from this telescope so far, including the discovery of very, very high redshift quasars from this telescope itself. So now a comparison of the two. So this is the deep field of Hubble Space Telescope that was observed using this one, and this is the same field that is observed with James Webb Space Telescope. So you can see the improvement in resolution that we have obtained, and you can see many, many lensed objects as well, which was not able to resolve using the Hubble Space Telescope deep fields. So this is what we do with improvement in telescope technology. We get better resolution, we get better images, and we get to probe deeper and deeper into the sky. So now this was the review of what telescopes we have as of now. Now, why do we need the upcoming facilities? So as I told you that better telescope will mean better resolution. So obviously better resolution will lead to our deeper understanding of the sky. We can probe deeper and we can probe earlier in the universe as well. And then obviously with the increase in technology, we have larger apertures. So larger aperture will again have the larger gathering area. So we can do much more precise sciences as compared to earlier techniques. Then obviously the larger telescopes will have more sky coverage, like you see in TESS. So TESS has 400 times more sky coverage than the Kepler mission. So as technology is advancing, so obviously telescope detector technology will also advance. So like 100 years ago, even a 1 meter class telescope was considered very, very state of the art, but now 1 meter telescopes are considered a toy. So, and then we can have more exoplanets as well because of the missions like TESS. And obviously with larger telescopes, we can probe the universe closer to the Big Bang because we are looking deeper and deeper into the sky. And now with the multi-messenger astronomy into picture, so we can have synergy with different observatories like LIGO, Event Horizon, and then the telescope local, the global network of telescopes are there which can probe the sky 24/7. So if there is day in India, you can always have a telescope in the US which is observing for you, and vice versa. If there is day in the USA, you can observe through India. So this is the global network of telescopes that can operate simultaneously. And similarly, we can have the upgrades to current and ground-based gravitational wave detectors. So like LIGO, you can always make more precise instruments to the development in technology. So the most awaited and most earliest the telescope that will be coming up is the VRO, which is known as the Vera Rubin Observatory, or the Large Synoptic Survey Telescope. So this telescope will have the 8-meter primary mirror, but then you will say, what is new in this? because we already have the multiple 10-meter class telescopes. But this 8-meter telescope will survey the sky every few nights in 6 bands. So none of the 10-meter class telescope is designed to be a survey telescope. This telescope is itself designed to be a survey, as 90% of the time would be dedicated to survey. So first light was expected earlier in 2023, but again things got delayed due to COVID. So maybe a couple of years here and there. So we now expect the first light to be in 24 or 25. And you see the mirror sign. The scientists were sitting inside the mirror diameter here. So you can imagine the kind of scale that we are talking about. So this telescope is currently under construction. We can expect it in 2027, 4 years from now. So this will have the 39.3-meter diameter. This is the largest telescope ever. And you can imagine what can we do with this telescope. So you can resolve two light sources 30 centimeters apart, roughly at 12,000 kilometers. So you take two light bulbs at 30 centimeters apart, you can easily resolve them from 12,000 kilometers. So this kind of resolution and precision we have from this telescope. The first light is planned for 2027. It is operated by the European Southern Observatory, and obviously it will probe the early universe and also attempt to direct image the exoplanets, which will be detected by the space missions like TESS. Then the Americans have this GMT coming up. So the GMT is a very unique kind of telescope. So each of the segments is 8 meters across. So this will be like 30 meter, about 24.5 meter. So all these segments will combine to form a single telescope, and it is led by the US with 5 other partner countries. The goal is to find exoplanets, explore the formation of first stars, galaxies, and black holes. Now, another telescope that is coming up is the 30-meter telescope. It is planned to be set up in the Monarchy Observatory in Hawaii, and it is a multinational collaboration which includes India and China as partners. And it was supposed to be the first telescope that is beyond 10 meters, but again, unfortunately, the construction was halted in 2015 due to local protest, and construction has not resumed as of now. So the European telescope, the ELT, will be probably will be leading this telescope. But again, this telescope will be something will be sometime up in this decade. That's what we expect. And if you talk about the space telescope, so a very new telescope that is going up in space next year probably is the Chinese Space Survey Telescope. It is the 2-meter telescope with the diameter 2-meter telescope with a primary mirror of about 2 meters. So it's the almost same size as Hubble, but you can see the improvement in telescope technology. With the same size of telescope, we can have 300 times larger field of view. So Hubble was launched in 1990. This is going in 2024. So in 34 years, you can imagine the kind of leap that we've made in technology, that with the same size, you can observe 300 times larger field of view. And it will be docked to the Chinese space station. So this part that you see, this will be docked to the Chinese space station itself. So you know that Chinese space station is already up in space, and it will be launched in 2024 by the NAOC. And the primary job is to conduct a 10-year survey of the sky with a limited magnitude of 26 magnitudes in photometry and 23 in spectroscopy. So this will be again providing a large amount of data to the survey data kind of thing to the public. Similarly, the optical IR telescope that is going up in space is the Nancy Grace Roman telescope. This is again operated by the US, same size, but 100x larger field of view as compared to the Hubble Space Telescope. And this will go to the L2 Lagrange point near the James Webb Space Telescope. So this will continuously monitor the sky. And this is proposed to be launched by NASA in 2027. So 4 years from now, you can expect this telescope in space. And the Europeans will have this a new telescope that is known as Athena, Advanced Telescope for High Energy Astrophysics. It will operate in the energy range of 0.2 to 12 kilo electron volts, which have focal length of 12 meters. And it can do both imaging and spectroscopy in the X-ray wavelengths. And it will again be located at L2 Lagrange point near the James Webb Telescope to understand the universe. If you talk about the radio, so a very new telescope is being set up. So it is already operational partly. This is the International Telescope built in Australia and South Africa, and it will have a total collecting area of about 1 square kilometer. So this is why this is known as the square kilometer array. So you can imagine if you stand here, so all across 1 kilometer you will only have these dishes, and it is a consortium of 14 countries. India is also a part of this thing, and the first light is projected in 2027. So all the arrays will be set up in the next couple of years, 3 years from now. So you can see what kind of these dishes are there. So you have the dense aperture arrays, you have the sparse arrays, and you have the dishes here. And this diameter is about 5 kilometers. So this entire array is being set up in South Africa and partly in Australia also. Now, if you talk about the Indian contribution, unfortunately, we do not have the 10-meter class telescope as yet, but work is going on. So now we have multiple, but again, it's not that if you don't have a 10-meter class telescope, you are outdated or something. But you can do good science with 4-meter class telescopes as well. So we have multiple telescopes across the country. The largest one is a 4-meter class telescope located at JWST in Aries, where I work. And apart from that, we have the 2-meter telescope located in Ladakh. And Aries also has a 4-meter liquid mirror telescope that is coming up. Obviously, two small telescopes we have. And then in infrared observatory, we have in Mount Abu, we have an infrared observatory which is setting up a 2.4-meter class telescope. In Ayuka, we have a 2-meter class telescope. Then we have a 2.3-meter telescope at the Vainu Telescope Observatory in Kavlur. And then obviously we have the GMRT in Pune, and Astrosat is there in the sky. So these are the facilities that we have currently. And this is the Devastal Observatory that we have in Aries. So all three telescopes are located at the site itself. You are all welcome to visit here if you want to. This is the 4-meter survey telescope that is the liquid mirror one that is operational now, inaugurated last year itself. This is a 3.6-meter telescope inaugurated in 2016, 7 years ago. And this is the small one, 1.3-meter that we have at Devastal. Now, how do we contribute to the large upcoming telescope? Because India has a huge potential in terms of astronomy. So Ayuka is a partner of the SALT. This is a 10-meter telescope in South Africa. So Ayuka gets some reserve time from the SALT observations and has helped in development of the telescope itself. We have an active participation in the 30-meter class telescope, the TMT. So there is a very, very active research lab in Bangalore, which is taking part in the mirror design and instrument design for the 30-meter telescope. And India is also a participant in the square kilometer array. So once the SK will be there, obviously India will get some guaranteed time. And then there is an announcement of LIGO India. So it will be set up somewhere near Pune itself. So we will have our own gravitational wave observatory. And a 10-meter class telescope is also being proposed. So maybe in some time from now, we will have a 10-meter class telescope in India itself. Okay, so now with this, I summarize what are take-home points for you. So telescopes have increased in size over time, and this trend will obviously continue in the decade because with increasing technology, we are increasing the telescope size. So this is a rough plot of the telescope aperture that we have. So in 1600, 1 dm, I mean decimeter. So this is imperial units, less than about 10 centimeters. So in 1600, we have this size, 1700 you can see, and now we are exploding in size. So we are somewhere here, and this is already reaching up to 100, but we cannot reach 100 right now. So we are near 40 meters in 2030 or so far. And multi-messenger astronomy is the norm, as has been with the gravitational wave detection in recent past. So gravitational wave could not be detected through only the LIGO itself, because once the gravitational wave is triggered, you have to follow up with the optical. We have to follow up with the space-based telescope to confirm whether this is coming from the black hole merger or not. And India is a part of the handful of few major projects like the SK and the TMT, and it is possible that we'll have a 10-meter class telescope in our country in the near future. So that's it from my side, and this is a view that you get from the our own observatory in Aries. This is a nice view of the Milky Way over there, and this is the Sampurna telescope that we have at our campus in Manor. Thank you.
Thank you, sir. So, do you have any question to Mr. Vivek Kumar Jha? You can ask.
Uh, good evening, sir. Am I audible?
Yeah.
Sir, my name is Chandra X-ray. I am pursuing BTech Aerospace Engineering. This is my final year. Sir, my question is how Hohmann transfer is related to Aditya 11. Like we are using Hohmann transfer to put our Aditya 11 to 11 point, right?
Mm-hmm.
So how can we what will be the orbit?
I see.
Indirectly, I'm asking what will be the trajectory for the Aditya 11.
I see. So actually, I'm not very sure about the Aditya L1 trajectory, but how this works, I can explain. So, like you launch the craft into space, so it will be in some orbit around the Earth, right? Because you are not giving it the escape velocity. So it will be in some orbit around the Earth, and then when it comes to the same point, you just give it a booster. So the orbit will increase with time. So this is what they do with other, like if you go talk about the Chandrayaan. So what they did, that the orbit was assisted step by step, they were accelerated, and the orbit was so large that it fell into the gravity of the moon itself. So, but in Aditya, things are a bit complicated because you're talking about 1.5 million kilometers here. So I guess this will be a gravity assist would be there, and then the thing will be boosted into the L1 orbit that is there. So once it is in the orbit, it can propagate itself because it has been given a boost from the Earth itself, from the this orbit itself. So that's when it will propagate, and then once it reaches the L1 point, it will be there in the stable orbit. That's what I think.
Okay, sir. Thank you. Got it.
Yeah.
Anyone else?
I
Did
see.
anyone had any question?
I see a question in the chat box. Okay, which telescope for beginners, for students? Oh, well, it depends on what kind of student you are. Like if you are in a school, so you can always participate in telescope workshops. And if you are a bit more interested, you can always buy telescopes like 4 to 5 inches from multiple organizations that are there in the country. So I think you can go ahead with the 5 to 5 inch telescope. Will be good for the beginners to understand the local sky and all.
Good evening, sir.
Yeah.
Sir, any citizen science projects related to Indian project where common people can participate?
Yeah, so in India, I'm aware of a few projects like you might be heard about this RAD at Home program. You know that?
Anand hota, sir.
Yeah, so RAD at Home program is there in Bombay, so Mumbai, so he is doing it. And apart from that, there is a SSERD kind of organization which is doing the asteroid search and all. So that program is there, and obviously you can join the Zooniverse project itself because Zooniverse it's not Indian per se, but it is run by the global community. Indians also part of it. So Zooniverse is there. And then there is a Galaxy Zoo also, I guess. So Galaxy Zoo is, but again, these are not originated in India, right? So I think 2 or 3 projects I'm aware of. The one is the Red at Home, SSRD is there, and yeah.
Okay, sir.
So there are a few questions in the chat. Okay, can we visit all telescope places in India? Oh, of course you can. If you just need some prior appointments at some places. Just call or send a mail to someone who will be responsible. Like in Aries, I can tell you that you can definitely visit all the telescopes. You can just send a mail to in Aries website we have a section which is known as apply for a visit. So you can always apply for a visit, and if there is someone available, they can all show you telescope and all. Explain all the things as well. There is no problem. I'm sure you can do in GMRT also. Since we're getting lots of data.
Okay. Hello everyone. My name is John Maskin-Laus. I'm from Haiti. Okay, my question is it possible to transform a satellite dish that has a little diameter into a radio telescope? This is my question.
Yes, so we are talking about citizen science projects here. So this is a very, very good citizen science project. I think there are multiple people who have already done this. So if you explore a bit, you can find that you can just need to fine tune your this receiver, and the dish is anyways catching radio wavelengths only, because what you are seeing on your TV is radio emission itself. So it can always do it can, but you just need to tune a bit, because it is tuned to your particular frequency that you're watching to your television. So if you can tune the frequency a bit, you can always convert your this dish into a radio telescope, because that's what all
Okay.
radio telescopes are. They are just dishes, nothing else.
Okay, thank you.
Yeah. So, okay, some more questions. Since we are getting a lot of data from all the observatories situated in India, are we planning something like citizen? So there are people who are already doing citizen science with the data that is in India. You can look at the Red at Home program. They are doing, very good science with the all radio data that is available. How can you visit Ayuka, Pune, or GMRT? I think I already told you. You can just apply. You can look at the website.
Hello, sir.
Yeah.
Sir, my name is Labuni Mondol. I'm a student. Sir, how can I join the aerospace project?
How can you join the aerospace project?
Yeah.
I'm not an expert on aerospace. I mean, I cannot help you with that. Maybe someone who is an expert in aerospace here, they can tell, because we do astronomy, right? So what do you mean by aerospace project? I mean, you just want to do some internship and all, or are you interested in a career in aerospace? Can you hear me? Okay. So, can normal telescope capture Saturn and Jupiter also? Yes, of course, you can observe Saturn and Jupiter with the normal telescopes. It's not difficult. Just need to look at the sky and just position your telescope there.
Okay. Sir, actually, I also have a question. That what is actually the difference between the survey telescope and normal telescope? I think
Yeah. Okay.
the explanation will clear the concept for the participant.
Yeah, that is a good question. So basically, the telescope can operate in two modes. So one is you look at a patch of the sky, and then you do your science from that. And another approach would be you look at a patch of sky every day or every other day for say 3 years, 5 years, and then do your science from that. So you're looking at single object multiple times, right? So the survey telescope would be like it would be in the second category. So it is looking at a particular patch of sky or a particular pattern in the sky, and is looking at it repeatedly. So it's not like, and in survey, the other difference is that in normal telescopes, which are not survey, so basically you apply for some time, then you get a few hours or a few nights. While in survey telescopes, you don't apply for time. So they will do the survey and then they will give you the data publicly whenever that is available. So an example would be the Sloan digital survey. So HDSS is an all sky survey. So it's a 2 meter class telescope to scan the entire sky for almost 20 years right now. So you get all the data from there publicly. So you're not talking about the single objects here. So the survey telescope can scan the entire region of sky at once. So you can observe multiple objects in a single time through the survey telescopes. While in the normal telescope, you have to apply for a time, you have to look for an object or list of objects, then only you can do your science from that.
Hello, sir.
Okay, thank you.
Yeah.
Anyone
Uh,
have any question?
how can I acquire the data from this satellite, these telescopes, and can I use it for personal PhD program or any project?
Yeah, obviously that's what everyone does. I mean, if you have a PhD project, so basically it will work like that. So you have your supervisor will be you will discuss it with the supervisor itself. So your supervisor, you and your supervisor will design a program, and then you will either apply for time. So once you get the time, you can observe, you can have your own observations, and then get the data and do your science with that. Or you can use the survey data like we do. Like you can look for the all sky surveys, and then you try to look for your objects whether they are in the sky or not, and then you can get the data from there. So that's what I mean professional astronomers are doing right now. This
Uh,
data is
can I use can I use it for personal use in personal projects?
I mean, whatever data is public, you can always use for your personal projects. There is no limitation as such. If the data is public, it's for the public use. I mean, there is no reason why you will not be able to do it.
Okay, and can I request for a specific data like geology of Mars and all for study purpose?
Well, for that you just need to see whether the data is already public or not. So you can have a look at the NASA data that is publicly available on the website, and then you can see whether they are giving it publicly or not. I'm not aware about Mars because I don't work in that regime. Maybe someone who's an expert in that can help you with that.
Okay, thank you, sir.
Why most of the colleges cannot establish their own telescopes on their campus for bachelors? Oh, that is a very good question. I mean, if you are in a college, you should talk with your principal regarding that. I mean, why they are not doing it. I mean, telescope setting up a telescope is not a very costly thing. You can always do it. You can always have a small observatory on your own campus. So maybe your teachers are not motivated enough. You know? So this is why I mean we are having talks like this to motivate your teachers and all. You can always set up. Can BTech students apply for ride at home? Yeah, obviously BTech students can do. I mean, there is a Facebook group, and you can join the Facebook group there, and you can continue. Most of the ride at home projects are led by BTech students only. You can just look for them on Facebook.
else? Anyone else has any question?
Okay, can you share your PPT? Okay, I can share with the organizers. You can discuss with them. How can I become astronomer for BSc in physics? So after BSc, you need to apply for MSc program, and then you can join a PhD program somewhere in the astronomical institutes in India, like IUCA, ARIES, or IA. Then you can become an astronomer. Can IT students participate in CSP? I don't know what CSP is. Can you explain, or can you just elaborate what CSP is?
Okay, I have a last one question. I want to know what is the difference when you observe the sky with an optic telescope, if I can say that, and with your telescope. What is
Okay.
the difference?
Okay. So in optical telescopes, this is basically you just look at the image, and this is what you see from the naked eye itself. Like on the left, you're seeing. So this is an image of all the stars, and you see, and this is exactly what you'll see through a telescope, right? I mean, you can have a bit fainter things. You can observe a few more fainter things from the telescope, but when you're looking at the stars only. While in radio, basically, you are not looking at the stars directly. In radio wavelength, things are very different. And if you try to reduce the radio data, you are talking about the contours and all. So radio is basically all about the intensities. It's not about the photons that you're seeing in the sky. So in radio, you have all intensities, and you're not, I mean, getting photons as such directly as you're getting in the optical. So it will be intensities, and then you try to understand those intensities in terms of contours and all. So radio is a bit different as compared to optical.
Okay, thank you.
MSc in physics is better. MSc in astronomy is better. So actually, MSc in astronomy is not offered in many places in India, at least as far as I'm aware. Only one or two universities are providing MSc in astronomy. So the most likely would be for you to do an MSc in physics, and then obviously go for astronomy as for your PhD if you're interested in astronomy itself. When 3D mapping of galaxy completed by Gaia mission. Okay, so it was completed maybe a couple of years back or maybe last year, because the data came out in 2023 only. The new data release DR3, I guess. So it was completed somewhere in the last couple of years itself.
Anyone else has any question? You can uh, ask us, sir.
I'll just type my email here in case you are interested, anyone interested in communicating further. So this is my email, and if anyone is interested, you can just note it down and then send an email to me, and maybe we can just have a talk later after this, if that's possible.
Anyone has any question?
Sir, how can I get a project in Aries?
Sorry, can you be louder? I did not get your question.
How can I get a astronomy project in Aries?
In Aries. Oh, okay, okay. So it depends on what stage you are. So what stage you are right now in your academics?
I have completed my BSc.
You're doing your BSc. Oh, that's fine. So during your BSc, if you have some free time, like especially when your semesters are getting over, so you can always mail someone, some scientist in Aries, that you are a BSc student and this, and you just want to do a project. So if there are some slots available, they can respond, and then you can obviously look at the website. So we have this Aries Training School in Astronomy at SOA, which is held every year in months of April or May. So you can join at SOA, and then you can get in touch with the people there. So the idea is to send emails to scientists and then see how they respond. If there are slots available, they will respond definitely.
Okay, sir. Thank you so much.
Oh, there is no best book as such. You can just explore and you can see whatever you like. There is no best or worst as such. It depends on your personal taste itself. Yeah. So I guess there are no
Okay, sir.
further questions.
And I actually have a last question
Yeah.
because some of the viewers actually asked me those things that what is actually the minimum millimeter diameter telescope we need to clearly see the Jupiter's moon, or Saturn and their moons? What is actually the minimum diameter needed to see those things? At least clearly that okay, they are actually visible.
Okay, so actually it depends on a couple of things, not only the aperture of your telescope, but rather the location of your sky as well. Like if you are in a city, so you cannot even look at the Jupiter with a 6 or 7 inch telescope. Well, if you're in the Himalayas, even if a binocular is fine for you to look at the Jupiter. But if you are talking about, so obviously when you are doing astronomy, you will not be doing it from the city itself. So you will be in some far off place where the sky is clearly visible. So I think 4 to 5 inches would be fine to do, because we have looked at Jupiter and Saturn from 5 inch telescope and they look just fine. I mean, you can make out the rings and all. You can look at the moons of Jupiter with a 5 inch telescope. So yeah, 5 inch telescope will be fine.
Okay, I have another. I said I had a last one question, but this is really the, I can say, the last. Okay, when I use, for example, the
Mhm.
Stellarium app to navigate in the sky,
Yeah.
what I see, for example, when I zoom on the moon,
Mhm.
it is the real image I see in real time, or it is another thing. Uh,
No, no. So basically, what a stellarium does, it. Okay, so forget stellarium. Do you use some navigation, some maps on your mobile, on your cell phone?
yeah,
And
on
do no,
Stellarium app.
I'm talking about maps. So you use Google Maps on your cell phone?
Yep, I use it.
Okay, so if you look at the satellite view from Google Maps, you can see your home, right?
Yes.
Yeah. So, but
No,
that's not a real picture of your home itself, right? Yeah. So that's how it works in Stellium also. So basically, it takes a snapshot of the sky every few months or every few weeks. It depends on the patch of sky you're looking at, and then it updates it to the software itself, like it's exactly like the Google Earth does with you. So you're looking at your home, but then it was taken at some earlier date itself. So similarly, it works with Stellium also.
I understand.
Yeah. Who is the father of astronomy in India? It's a very difficult question to answer. I mean, I don't have an answer to this question. There are multiple people who have contributed different things. So you cannot pinpoint a single person who is the father or something like that. I'll recommend a book to you. Typing in the chat, you can just find this book. It will be beneficial for you. Space Life Matter. This book will answer a lot of your questions like this. Yeah. So, any other questions?
Anyone has any questions?
India is better abroad for astronomy. So abroad is a very very wide term. I mean, it's not like there is in India, there is abroad. I mean, each India also has some very good facilities, and abroad also has some very. It depends on the kind of thing you want to do. There's no such thing as better or worse in this.
Anyone has any question? Okay, someone asks that is this webinar will be recorded? Yes, I will record the webinar. Actually, the webinar is recorded, and I will upload it to YouTube, and then I will share the YouTube link there, so you can see it later.
So I guess there are no further questions. So I'll just make a concluding remarks to all. I mean, people. I think there are people from different educational backgrounds and different education levels in this audience. So I mean, astronomy is a science which is open to all. I mean, it's not that you are limited by you're only limited by your imagination. So whatever career stage you are in right now, you can always do astronomy. You can just get a telescope. You can visit anyone who has a telescope and just explore the sky. So astronomy is not limited by anything. Obviously, when you want to do astrophysics, then you have to be a professional astronomer and all. But if you just want to do astronomy, look at the sky, just wonder about the stars and all, you can always do it at any career stage of your life. So it's an open thing for all. There's no limitations. So I guess there are no more questions and all. So I again thank the organizers for your opportunity to present a talk here. And that's it. So I guess that's it. So shall I take a leave now?
Yes, so thank you, sir, for your speech. And I think the participant will get their answer and get a understanding of the astronomy and what are the telescope. So thank you, sir, for your speech. And so now we finish the webinar here. So participant can leave the webinar now. Thank you and good night.
Okay. Thanks for the opportunity. Thank you.